All right, welcome to day 11. You got your homework listed there at the top. Topic today will be linear approximation. There's your homework answer, so you could pause and check, and then I will pause the video for about 3 or 4 seconds on each of the worked out ones, so you can pause and see worked out solutions if you need them. Okay, so we're going to start out this video just with a few more practice ones of finding error in measurement, which we saw on yesterday's video. So we've got the measured length of the radius, 15 inches. Possible error is 1/2 inch, and we want to approximate the error in the volume in the surface area. So let's start out with volume. Volume is 4/3 pi r cubed. We'll take the derivative, dv over dr. That'll give us 4 pi r squared. Multiply the dr over. And we'll fill in. The r is the measured value of r, which was the 15 inches, times our plus and minus 1/2. And 15 squared, you got 225. 1/2 of 4 is 2, so 25 times 2, that'll give us plus and minus 450 pi inches. Now going over to the surface area, hopefully you remember surface area of a sphere formula is 4 pi r squared. So I'm going to skip a step. When we take the derivative and then multiply the dr over, we'll have derivative of surface area is equal to 8 pi r, and then eventually times the dr over there. So our differential for the surface area will have 8 pi times 15, our measured value of the radius, times that plus and minus 1/2. 1/2 8 is 4. 4 times 15 is 60. So we'll have plus and minus 60 pi. And in this case, we have inches squared because it's a surface area. Oops, so over here, actually, I forgot the cubed on our inches for the volume. So those, again, are simple ones. Little more challenging ones. So we got radius of a cylinder is 5 inches. Height is 3 inches. Possible error, 1/4 inch. We want the error in the volume and the surface area. So there's our volume. We're going to have to do a product rule, and we're going to try and do the shortcut. So remember, you could take the derivative with respect to either r, h, or some dummy variable. Let's say hypothetically we did it in terms of a dummy variable dx. So we'd have to do them each with implicit differentiation. Well, when you multiply by the dx, it would wipe out the bottom. So you end up, whenever you take the derivative of a thing, eventually it will end up as the d, that variable, at the end. So we're eventually going to get dv, derivative of pi r squared would be 2 pi r, and eventually we would get the dr there, times regular h, plus regular pi r squared times 1 times the dh. And again, just real quick, let's say, just if you're confused by that, let's say we did it in terms of x. We would have had 2 pi r times dr over dx times h plus pi r squared times 1 times dh over dx. When you multiply everything by dx, the dx's divide out, and that yields what we had over on the left there. So kind of the way to shortcut that is whatever variable you're taking the derivative of, it should end up with a times d that thing afterwards. So therefore, our volume will have dv is equal to 2 pi. Our measured value of the radius we have is 5. The dr is the plus or minus that 1/4 inch. The measured value of the height was 3 inches. plus pi times 5 squared times 1 times that plus and minus of a quarter. So we're going to get plus and minus 15 halves pi plus and minus 25 fourths pi. Again, we want the maximum error, so just worry about the plus or minus at the end. And we will get 55 over 4 pi. We got our plus and minus out front, and this was a volume, and we were in inches, so we have inches cubed. Now looking at the surface area. So surface area, you've got two circles, so 2 pi r squared. And then you've got the lateral area, which is the circumference times the height, so 2 pi rh. We're going to do our shortcut to get to the differential again. So we'll have dSA is equal to 4 pi r dr. Got to do a product rule here. We'll think of the times as being right there. So we're going to have 2 pi dr for the derivative, regular h, plus regular 2 pi r times 1 dh. So that's 4 pi. We'll have 5 times our plus and minus a quarter, plus 2 pi times the plus or minus a quarter, times the height of 3 inches, plus 2 pi, the radius of 5 inches, times the plus or minus a quarter. So we're going to have plus or minus 5 pi. A quarter and a 4 will multiply to 1. We'll have plus or minus 3 halves pi. Plus or minus 5 halves pi. And this then will give us, for the differential for the surface area, plus or minus 9 pi. And because it's a surface area, that would be inches squared. So hopefully between yesterday and those couple examples, you feel pretty comfortable with doing differentials to find your approximated error. So another way to go about this is doing linear approximation. So linear approximation, it's essentially doing the same thing as differentials, but finding, instead of just the change, it's finding the y value of the tangent line. So it's using the y value of the tangent line to estimate the y value of the curve when you move a little bit away from your point of tangency. So basically what we had from yesterday is this part in the red, that our differential is the same as f prime x times dx. So that slope of the tangent line at the point of tangency times the little bit of change in x value. Well, if you apply the change, so here's the change, if you apply that to the y value at the point of tangency, that will then give you an approximation of your new y value. So this is the new y. So the new y value can be approximated by taking the y value at the point of tangency plus our differential. So we can use that idea here. So we got to think, what would be our point of tangency that we would want to use if we want cube root of 66? Well, first off, the function we're going to work with is cubed root of x. We want to think of what's a nice cubed root close to 66, and that would be 64. And the cubed root of it is 4. So we'll have to take our derivative. So this will be 1/3 x to the minus 2/3. So dy is really 1 over 3x to the 2/3 times dx. And that's going to be this part here. The f of x is the nice y value at that point of tangency. So we're going to have 4 plus, and why don't we write here that cubed root of 66 is approximately that. 4 plus, and we're just going to fill in that differential. So 1 over 3 times 64 to the 2/3 times our dx, our little bit of change in x. Well, from the nice x value, we move 2 to the right, so that's times 2. So this will give us 4 plus, cube root of 64 is 4, 4 squared is 16, 16 times 3 is 48. So this is 1 over 48 times 2. So that's 2/48, or in other words, 1/24. And add that with the 4, and you can either have 4 and 1/24, or that's the same as 97 over 24. Now, here's another way to think of the linear approximation. Think of your point slope form of a line. We have y minus y1 is equal to a slope times x minus x1. Last year with Mr. DeLands, you guys did equations of tangent lines. Well, let's think about what the equation of this tangent line would be. Our y1 would be 4, and our x1 would be 64, because that's the point of tangency. And then the m is just the slope of that point of tangency, which was that 1 over 48 that we found here. The derivative with it all filled in. Well, what we're trying to find is we're trying to find this y value here. And we can get that by subbing the 66 in there. Well, 66 minus 64 is 2. Notice that matches this. 2 times 1 over 48 gives us the 1 over 24. And then you would just add the 4 over. So then we would get y is equal to the 4 and 1/24. So what we used here is just point slope form with the y solved by itself. So we basically moved everything over already, so we wouldn't have to rearrange it. But if you like to do this type of thing with linear approximation, and so you can see it like that, and then just add your 4 over or whatever it ends up being, it's the same idea. So you could do that as well. Now, this graph, notice, is concave down, so the tangent line is on top. So this would be an overestimate. And we can say, since f of x is concave down. All right, so our next one, we're going to use linear approximation again to estimate sine of 190 degrees. Well, something close to 190 that's nice is 180. But remember, we always need to work in radians, so we're going to work with pi, and sine of pi is 0. So we need to think of what we're really estimating in terms of radians. So to convert to radians, just multiply by pi over 180. So this is really sine of 19 pi over 18 that we want to find. So our f of x is the y value of our point of tangency, which is the 0 that we had up here, plus the f of x we're working with is sine x. So our differential is just cos x dx. So we will fill in pi to cos x, and that'll give us our -1. Our differential, how much did we change by? Well, our nice x value was just pi. 19 pi over 18 is adding pi over 18 to that. And when we do that out, we get negative pi over 18 as the approximate estimate of sine of 190 degrees. And notice it's a little bit to the right of 180. So it makes sense that it's a negative value. It's below the x-axis. So just real quick, we'll one last time show you the tangent line, equation of the tangent line all the way out if you didn't like it already on one side. So we would have had y minus 0 is equal to our slope at pi was negative 1, and then we would have x minus pi. So all we did was sub pi over 18 in there, and you didn't even have to add anything over in this case. We get the negative 1 pi over 18. Okay, so that's doing it not already rearranged. But by doing it the rearranged way, it just saves a little bit of time. All right, so we're going to use linear approximation to estimate radical 23. So we're going to work with the equation y equals square root of x. Our point of tangency that is nice nearby would be 25 in for x, meaning we get back 5. So this part here is just going to be 5. That's the y value at the point of tangency. Our differential will end up being 1 over 2 radical x dx. So if we sub in our 25 here, our x value of our point of tangency, we get back a tenth times the dx, what we're changing by. Well, our x value at the point of tangency is 25. We're going 23, so that's 2 to the left, so we're doing a negative 2. So this will be 5 minus 1/5. So either 4 and 4/5 or 24/5. And that is the approximate value of square root of 23. This, again, would be an overestimate, since f of x is concave down. All right, let's see if we can do a similar idea. If our equation, we would have to use implicit differentiation. Okay, it's not explicit because we don't have y by itself, and we can't get y by itself. So 3, 1 we can see lies on the graph there. You could also confirm that if you wanted by subbing in. You would get 1 plus 3 times 1 cubed, which would give you 4, and on the right you would have 3 squared, which is 9, minus 5 is 4. So that does check out. So we want to estimate the y value when x is 3.06. Well, remember our setup. We're looking for f of x plus f prime of x dx. Well, f of x is just the y value at the point of tangency. So that's 1. That's the 1 from the 3, 1. Plus, we're going to have to figure that value out. But then dx, we know, is just 0.06, which is 600ths, or in other words, 3/50ths, because fractions are usually easier to work with than decimals. So let's do our derivative off to the side. We're doing the derivative with respect to x. So the derivative of y would be dy over dx. Plus, we got a product rule. Derivative of x is 1 times regular y cubed plus x times 3y squared dy over dx is equal to 2x, and then derivative of negative 5 is 0. So we want to find what is the value of dy over dx at this point. So let's go ahead and fill in for all the x's and y's. I think personally, when you know the point, it's easier to sub those in now than getting dy dx by itself and then rearranging. So we have 1 times y cubed, so we're going to have 1 times 1 cubed, plus our x value is 3 times 1 squared, dy over dx equals 2 times 3. So this would give us dy over dx plus 1 minus, sorry, not minus, plus 9 dy over dx is equal to 6. We can subtract the 1 over and get 5 over on this side. And that would be 1 dy over dx plus 9 dy over dx's to give us 10 dy over dx's. And then dy over dx would just equal 1/2. Now, in this case, that dy over dx is specifically representing f prime at 3 comma 1. So that's the specific numerical value of the slope of the tangent line, which is what goes right here. So this is going to be 1 plus 3 over 100. And you can either do 1 300ths or 1.03. So that is the approximate y value. And from the graph, you can see it looks like the function is increasing there. So that seems to make sense. So I want you to think about, just from the graph, is that value an overestimate or an underestimate? And something you can try as a bonus, and you can email to me before class tomorrow, is see if you can prove analytically whether this last one is an overestimate or underestimate. So what that means is you need some type of calculations to back up why it is an overestimate or an underestimate. It can't just be looking at a graph to determine it. You need some type of calculation. So see, if you'd like to do that, you could email your work for that, take a picture and email it for bonus credit.